This is SpaceTime Series 19, Episode 75, for broadcast on October the 26th, 2016. SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe. You can download SpaceTime as a free twice-weekly podcast just about everywhere, including iTunes, Stitcher, Pocket Casts, Bytes.com, YouTube, SoundCloud, Audio Boom, and from spacetimewithstuartgary.com. The show's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C. Coming up on SpaceTime, new questions about dark energy and the ultimate fate of the universe, the most volcanically active world in the solar system, and investigations now underway to try and determine why the Mars lander crashed and burned. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
A new study of exploding stars has raised fresh questions about the existence of dark energy, a mysterious force causing the expansion of the universe to accelerate at a faster and faster rate. The new findings, reported in the journal Nature, could have important implications for the ultimate fate of the universe. 5 years ago, the Nobel Prize in Physics was awarded to Brian Schmidt, Saul Perlmutter and Adam Rees for their discovery that the universe is expanding at an ever-accelerating pace. The discovery also won the trio the Gruber Cosmology Prize and the Breakthrough Prize in Fundamental Physics. Their conclusions were based on an analysis of Type 1a supernovae, the spectacular thermonuclear explosions of dying stars similar to the Sun. A single thermonuclear or Type 1a supernova can emit as much light as an entire galaxy, and more importantly, they all explode with a similar level of luminosity. Consequently, by knowing how bright a supernova should be compared to how bright it appears, astronomers can work out just how far away it really is. These Type 1a supernovae can therefore be used as standard candles, literally cosmic distance markers to determine how far away objects are. The Nobel laureates found over 50 distant supernovae whose light was far weaker than expected, a sign that the expansion of the universe was accelerating. For almost a century, thanks to Edwin Hubble, the universe has been known to be expanding as a consequence of the Big Bang 13.8 billion years ago. That rate of expansion has important consequences for the ultimate fate of the cosmos. You see, a universe with just the right amount of matter and gravity would expand at a consistent rate, driven by the force of the Big Bang itself. On the other hand, if the expansion of the cosmos equals the gravitational impact of matter, that expansion of the universe will eventually coast to a stop, resulting in a static or steady-state universe. Then again, a universe with slightly more matter and gravity would not only stop expanding, but it could eventually start to contract, resulting in a scenario which astronomers refer to as the Big Crunch. Now, a Big Crunch could lead to another Big Bang, followed by another Big Crunch, and so on. However, discovery that the universe's rate of expansion has been accelerating means that some invisible unknown force, a force which astronomers have now named dark energy, must be present to drive this accelerated expansion. Depending how powerful dark energy is, the universe will either keep expanding, with galaxies eventually moving further and further away from each other, ultimately leaving a night sky looking dark and lonely, with all the stars and even neighbouring galaxies too far away to be seen. This would result in a cold, dark universe and a scenario which astronomers refer to as the Big Freeze. However, there's a much more disturbing scenario out there, one which would occur if dark energy is getting stronger, as it appears to be. This wouldn't just result in all the galaxies disappearing over the cosmic horizon, but it would also cause all the stars in our own galaxy to move away from each other, eventually even causing the planets to move away from the stars, molecules to split apart into their constituent atoms, and even atoms to rip apart into their subatomic components, resulting in a universe of nothing more than a sparse collection of free-floating elemental particles, such as electrons, quarks, neutrinos, and photons, a scenario known as the Big Rip. It's these ultimate big questions which are making dark energy such an important and significant enigma, perhaps the greatest in physics today. The original Nobel Prize-winning discovery led to the widespread acceptance of the idea that the universe is dominated by dark energy. What is known is that dark energy constitutes about 3/4 of all the energy in the universe. This mantra has now become the standard model of cosmology. Therefore, the findings of the 2011 Physics Nobel Prize have helped unveil a universe that, to a large extent, is unknown to science. Now a team of scientists led by Professor Subir Sharkar from Oxford University has cast doubt on the standard cosmological model. Making use of a vastly increased data set, a catalogue of 740 Type 1a supernovae, more than 10 times the original sample size, the researchers have found that the evidence for the accelerated expansion of the universe may be somewhat flimsier than previously thought. In fact, this new data is consistent with a constant rather than accelerating rate of expansion. Sharkar says the original findings came with only a 3 sigma level of confidence, far shorter than the 5 sigma standard normally required to claim a discovery of fundamental significance. Sharkar says an analogous example in this context was the recent suggestion of the discovery of a new particle weighing 750 gigaelectron volts based on data from the Large Hadron Collider at CERN. It initially had an even higher 3.9 and 3.4 sigma in December last year, and stimulated over 500 theoretical papers. However, new data in August this year shows that significance has now dropped to less than 1 sigma. In reality, it had all been just a statistical fluctuation, and there was no such particle. Mind you, there is other data available that appears to support the idea of an accelerating universe, such as information in the cosmic microwave background radiation, the faint afterglow from the Big Bang, which was captured by the Planck satellite. However, Sharkar says all these tests are indirect, carried out in the framework of an assumed model, and the cosmic microwave background radiation itself is not directly affected by dark energy. Actually, there is a subtle effect known as the late integrated Sachs-Wolf effect, but it's not been convincingly detected. According to Albert Einstein's general theory of relativity, which describes gravity, radiation from the cosmic microwave background is stretched and bent as it travels through the voids and superclusters which make up the large-scale structure of the universe. And this stretching effect for dark energy causes a tiny change in the temperature of the cosmic microwave background radiation, depending on where it came from. Photons travelling through void should appear slightly colder than normal, while those arriving from superclusters should appear slightly hotter. Sharkar says it's quite possible that scientists are being misled, and the apparent manifestation of dark energy is simply a consequence of analysing the data in a simplified theoretical model, one that was in fact constructed in the 1930s, long before there was any real data. A more sophisticated theoretical framework, accounting for the observation that the universe is not exactly homogeneous and that its matter content may not be behaving as an ideal gas, 2 key assumptions of standard cosmology, may well be able to account for all observations without requiring dark energy at all. In fact, vacuum energy is something which science has absolutely no understanding of in fundamental theory. Sharkar says his team's findings serve to demonstrate that a key pillar of the standard cosmological model is rather shaky at best. A new study of Jupiter's moon Io has raised fresh questions about this most volcanically active world of the solar system. A report in the journal Icarus has identified some eruptions which seem to progress across the 3,600 kilometre wide moon's surface, progressively triggering one eruption after another, often up to 500 kilometres apart. Astronomers are at a loss to explain the sorts of mechanisms that could generate such progressive eruptions. The new findings are based on the longest series of frequent high-resolution observations of Io's thermal emissions ever obtained. The study's lead author, Catherine DeClaire from the University of California, Berkeley, says on a given night, astronomers were able to see half a dozen or more different hotspots. Of Io's hundreds of active volcanoes, DeClaire and colleagues were able to track the 50 which were the most powerful over the last few years. The authors observed both the heat coming off active eruptions and the cooling lava flows. They were able to determine the temperature and total power output of individual volcanic eruptions, as well as tracking their evolution over days, weeks, and sometimes even years. Io's volcanism is far more extreme than anything on Earth, and so it continues to both amaze and baffle scientists. What we do know is that Io's intense volcanic activity is powered by tidal heating, caused by friction generated deep in Io's interior as Jupiter's intense gravitational field stretches and squeezes the tiny moon by small amounts as it orbits the gas giant. Models for how this heating occurs predicts that most of Io's total volcanic activity should be emitted either near the poles or near the equator, depending on your preferred model. The simulations also indicate that the eruption pattern should be symmetric between the forward and backward facing hemispheres in Io's orbit. However, that wasn't what DeClaire and colleagues found. Over their extensive observational period, lasting from August 2013 to December 2015, the authors obtained images of Io on some 100 nights. They saw a surprising number of short-lived but intense eruptions that appeared suddenly and then subsided in just a matter of days. And interestingly, all of these occurred on the trailing face of Io alone, rather than also on the leading face, and they also occurred at much higher latitudes than for typical eruptions on Io. This distribution of eruptions is a poor match for what the models have been predicting. DeClaire says future observations should tell scientists whether this result is simply occurring because the sample size is too small, or whether it's because the models themselves are too simplified. Another possibility is that local geological factors on Io may be playing a far greater role in determining where and when volcanoes erupt than the impact tidal heating has. One target of extreme interest was Io's most powerful persistent volcano, Loki Patera, which brightens by a factor of more than 10 every 1 to 2 years. By the way, a patera is an irregular crater, usually volcanic in origin. Many scientists now believe Loki Patera is in fact a massive lava lake, and that these bright episodes represent its overturning crust, similar to what's seen in lava lakes on Earth. In fact, the heat emissions from Loki Patera appear to travel around the lake during each event, sort of like a wave moving around a lake, triggering the destabilization and sinking of portions of the crust. Prior to 2002, this front seemed to travel around a cool island in the centre of the lake in a counterclockwise direction. However, following the apparent cessation of brightening events after 2002, scientists observed renewed activity in 2009. But with this renewed activity, the waves began travelling clockwise around the lava lake instead of anti-clockwise. Meanwhile, another volcano, Kadaligong Patara, produced unusually hot eruptions twice during 2015, coinciding with a brightening of an extended cloud of neutral material orbiting Jupiter. This provides circumstantial evidence that the eruptions on the surface are the source of variability in this neutral cloud, although it's still unclear why other eruptions weren't also associated with brightenings. Using the near-infrared adaptive optics on two of the world's largest telescopes, the 10-metre Keck 2 and the 8-metre Gemini North, both located on the summit of the dormant volcano Mauna Kea in Hawaii, the University of California, Berkeley astronomers were able to track a total of 48 volcanic hotspots on Io's surface over 29 months. Adaptive optics are great because they can separate features a few hundred kilometres apart on Io's surface. Without these adaptive optics to remove atmospheric blur and sharpen the image, Io would be merely a fuzzy ball. The Keck and Gemini telescopes also complement each other. Gemini North's Q scheduling allows far more frequent observations, often several a week, while Keck's instruments are sensitive to longer wavelengths up to 5 microns, thereby allowing astronomers to detect cooler features such as older lava flows, which would be invisible in the Gemini observations. Officials with the European Space Agency are continuing to sift through data to try and determine exactly what caused last week's crash of the ExoMars Schiaparelli lander on the red planet's surface. Images from NASA's Mars Reconnaissance Orbiter identified new markings on the Martian landscape believed to be related to the probe's crash on October 19. The images show a bright spot, which is thought to be Schiaparelli's parachute, and a larger dark stain, interpreted as resulting from the impact of the lander itself. At this stage, mission managers are thinking the probe probably began its landing sequence too early, resulting in its thrusters switching off prematurely, causing the lander to drop a considerable distance down to the surface. The location data obtained by the Mars Reconnaissance Orbiter's Context camera will be used to obtain more detailed imaging of the site by the MRO's High-Resolution Imaging Science Experiment camera, HiRISE. The European Space Agency and NASA researchers are now analysing the images to try and glean as much information as they possibly can about the sequence of events that occurred during Schiaparelli's EDL, or Atmospheric Entry, Descent and Landing. What's known is that Schiaparelli entered the Martian atmosphere at 14:42 GMT for what should have been a 6-minute descent to the planet's surface. However, contact was lost shortly before the expected touchdown. The bright spot, thought to be the lander's 12-metre diameter parachute, was spotted 353.79 degrees east longitude and 2.07 degrees south latitude. That's an area which closely matches ESA's calculations for the landing location based on landing day data. It's also within the planned landing area, about 5.4 kilometres west of the centre of the landing target. The parachute would have been deployed during the second stage of Schiaparelli's descent, right after the initial heat shield entry. The parachute and the associated backshield were released from Schiaparelli prior to the final phase, during which the lander's 9 thrusters should have slowed the probe to a standstill just above the surface. However, the early data seems to indicate the landing sequence happened prematurely, with the parachute releasing early and Schiaparelli's landing rockets then also firing too early and consequently also cutting off too early as well. Estimates indicate that Schiaparelli dropped from a height of between 2 and 4 kilometres, therefore impacting the ground at a considerable speed greater than 300 kilometres per hour, as opposed to the rather gentle 4 kilometre per hour touchdown originally planned. The other new feature is a fuzzy dark patch roughly 15 by 40 metres in size and located about a kilometre north of the parachute. Mission managers think this could be Schiaparelli's actual impact site. The relatively large size of the feature could have been caused by disturbed surface material. It's also possible that the lander exploded on impact, as the thruster propellant tanks were likely still full. A closer look at these features will be taken next week with HiRISE, the highest resolution camera aboard the MRO. Since the module's descent trajectory was observed from 3 different locations, mission managers are fairly confident that they should be able to reconstruct the chain of events with great accuracy. Meanwhile, ESA teams are also continuing to decode the data extracted from Schiaparelli's descent signals. These signals were recorded by the lander's mothership, the ExoMars Trace Gas Orbiter. This should allow mission managers to establish correlations with measurements made by the Giant Meter Wave Radio Telescope Array in India and with the European Space Agency's Mars Express Orbiter. Mission managers say a substantial amount of extremely valuable Schiaparelli engineering data was relayed back to the ExoMars Trace Gas Orbiter during the descent and is now being carefully analysed by engineers. Meanwhile, the ExoMars Trace Gas Orbiter is currently on a 101,000 kilometre by 3,691 kilometre orbit with respect to the centre of the planet, and with an orbital period of 4.2 days well within the planned initial orbit. The spacecraft's working well and is slated to take science calibration data during 2 orbits next month. It'll then be ready for its planned aerobraking manoeuvres starting in March 2017 and continuing for most of the year. Aerobraking involves the probe regularly dipping into and out of the Martian atmosphere in order to slow down and circularise the orbit from its current highly elliptical trajectory to a 400 kilometre altitude circular orbit around Mars. The ExoMars Trace Gas Orbiter will then begin its primary mission, studying the Martian atmosphere, looking for, among other things, traces of methane. Methane's already been detected in the planet's atmosphere by both Mars probes and Earth-based observations. Although methane can be produced through geological activity associated with water, its most common source on Earth involves biological processes, and that's raising considerable excitement among astrobiologists who speculate that Martian methane could be a byproduct of subsurface bacteria, archaea, or other extremophile microbes. A state-of-the-art miniature satellite that will play an important role in developing Australian defence space capability is now ready for launch after successfully passing a set of gruelling tests designed to simulate the harsh environment of space. Engineers put the new Buccaneer satellite through its paces in 24/7 thermal cycling at the Australian National University's Mount Stromlo Space Environment Testing Facility. University of New South Wales Space Director Professor Russell Boyce says the new bird's the first of 2 being tested in a joint program to build Australian capability to develop and fly satellite missions. Buccaneer will perform calibration experiments for JORN, the Jindalee Over-the-Horizon Radar Network. It'll also contribute to the University of New South Wales Canberra Space Research Program, looking at ways to more accurately predict the orbits of space objects. Buccaneer will fly in low Earth orbit several hundred kilometres above the planet. Satellites and space debris can move around erratically due to space weather and atmospheric drag, even at high altitudes. These movements aren't well understood and so are hard to predict, making them a major potential threat for collisions. Being able to avoid such collisions is essential if nations are to safeguard the space-based technologies upon which the world depends. Buccaneer is a stepping stone to an increasingly sophisticated homegrown Australian space capability that can take advantage of rapidly transforming technologies in the Asia-Pacific space sector. An important aspect of the project is the desire to miniaturise scientific instruments, allowing smaller spacecraft to be used. Boyce says this should lead to new ways of inexpensively performing remote sensing, environmental monitoring, national security and improving communications links.
So Buccaneer is both a project and a satellite. From the project aspect, it's a joint collaboration, a research collaboration between Defence Science and Technology Group and UNSW Canberra. From DST Group's perspective, Buccaneer is part of a pathway towards both internal base know-how and capability within the organisation and a pathway towards greater and greater sovereign space capability within Department of Defence. From the university's perspective, it's also a part of a pathway towards capability, as well as being part of the what we call space situational awareness research that the university does.
This is important for things like JAWN, what we used to call the Jindalee Over-the-Horizon Radar, isn't it?
That's correct. JAWN is Australia's early warning radar system, and it operates by bouncing radar waves off the ionosphere. And the ionosphere is the ionised atmosphere up in space just above it. It's difficult to know what that's doing exactly at times. And so from Defence's point of view, from DST Group's point of view, they're seeking to understand what those radar signals look like up in space as they are interacting with the ionosphere. So they're trying to understand their system better and calibrate it better.
And of course, when we think about the ionosphere, it's the part of the atmosphere which is most reactive to geomagnetic storms from the sun. We just had a small one the other day. So even though we're now heading for solar minimum, we're still seeing some sort of geomagnetic storm space weather activity. And although all the atmosphere tends to puff up during these periods, it's the ionosphere which reacts the most, isn't it?
The ionosphere is very, very closely coupled to the entire base environment all the way from the sun to Earth. And it does affect satellites critically, partly by charging them up, and it can do disastrous things to them, but it also affects them because their orbits get perturbed and it becomes very, very difficult to predict those orbits and therefore avoid collision.
Drag.
Exactly, but it's not just drag. Drag is in the direction that you're travelling. There's also sideways forces, and the spacecraft and space junk end up wandering all over the place.
You're building 2 CubeSats. What will these do to monitor that? The
CubeSat will have, it's got onboard GPS and other sensors, so we'll know exactly where it is at all times. We'll also be watching it from the ground with the Space Surveillance Telescope that we have on our campus as it passes over. We're going to instruct the satellite to make prescribed movements, to rocket backwards and forwards in very known ways, and the sun will reflect off that and we'll collect that information on the ground, and that gives us some information about the way objects in space might be tumbling. We can use telescopes to record that information but not really know what we're doing. In this case, we're telling the spacecraft what to do and then recording that information. That gives us some information to validate simulations that we do that predict not just the orbits that these spacecraft do, but also the tumbling motion that they can sometimes.
Now, these CubeSats are pretty small. What's their dimensions?
The particular one is a 3-unit CubeSat, 10 centimetres by 10 centimetres by 30 centimetres. It's about the size of a loaf of bread.
How do you get something like that to move around in space? Does it have thrusters? Does it use gyrodynes?
This particular CubeSat does not have thrusters, although you can get propulsion units for CubeSats, and a later mission that we are planning will have thrusters on board. This particular CubeSat, though, it's got onboard gyros, reaction wheels, so it can change its orientation, but it can't propel itself, for example, from one orbit to another. Having said that, the fact that there is aerodynamic drag and aerodynamic side forces, it is possible to fine-tune the orbit simply by changing its attitude, effectively steering it around in the sky a little bit like an aeroplane.
So much for the Cayman line.
Exactly. It's the orbits, the motion that spacecraft and space junk undergo is sometimes quite chaotic. It's very hard to predict. You think you've got it today, you predict where it's going to be in a couple of days' time, and it's many kilometres away from that point. It's quite a risky situation for the world, actually.
And there's also the technology applications for this project from the Mount Stromlo point of view too, isn't there?
So Mount Stromlo provides the National Spacecraft Test Facilities at ANU's Advanced Instrumentation Technology Centre. So Australia has the capability to do all of the shakedown testing for quite large-sized satellites, probably beyond what Australia Australia would expect to develop and fly in the short to medium term, certainly preparing for the future. But yeah, we have world-class facilities to do that, and we've used those for testing Buccaneer.
And the University of New South Wales, that's really been pushing this entire CubeSat idea for many years now.
That's right. We've got colleagues at the main campus in Sydney who are engaged in working on CubeSats, but the activity at UNSW Canberra is really starting to change the conversation in this country, partly because of the investment that we've been able to make from internal cash, which is quite substantial. There's $10 million that we're investing over 5 years, and partly because of the team we've been able to assemble because of that. We've been bringing very talented and experienced Australians from the international space sector and bringing them back into one team. That gives us the capability and credibility to do quite sophisticated space missions, of which this one, despite the small size of the spacecraft, this is quite a sophisticated mission.
These are the sort of projects which advanced high school students, certainly university students, often put together that have flown piggyback on missions. Is there enough sophistication in something like this for professional satellite makers to learn?
Absolutely. The fact that this is a small spacecraft doesn't negate the fact that it is a spacecraft. If you're going to develop spacecraft properly, there's quite a process of professionalism and rigour and space systems engineering that needs to be applied to it. Most university and high school groups, they are both usually unaware of such processes, such lessons learnt from decades of international space experience, or even if they are aware, they do not have the experience, the know-how or the funds to implement them. What we're trying to do at UNSW Canberra is to apply exactly those processes, and we have people who've used them on running ESA and NASA programs. So this particular spacecraft, it might be small, but it's worth about $500,000 worth of kit. It's a very capable little spacecraft. It's been tested thoroughly. The flight software is very sophisticated, and it's a stepping stone to greater and greater things to come.
A couple of years ago, we were reporting, when SpaceTime was still called Star Stuff, we were reporting on a little project called FedSat.
Yes.
It ended up being built solely in Australia. The original carcass was to come from the UK, but something went wrong there, so we built our own carcass. We set the thing up. It was then launched, and it performed very well, but it turned out being a one-off project. All the talent and all the learning that came from that disappeared again. Projects like this that you're involved in now, it's designed to keep that talent here.
It is very much designed to keep that talent here. FedSat was a sad example of the fits and starts that space in Australia has had over the years. What's quite important is for government, and this is happening, for government to understand dependency on space and the need to invest domestically to build domestic capability, and then to see the need to invest in a series of missions, not just one here and one there. And so I think you'll see in the coming years that there will be a series of missions. Some of them will be defence-related, others will be non-defence, but they'll all be about building domestic capability and allowing local groups to acquire the skills and put their innovative technologies into orbit. But it's got to be done in a rigorous, very, very structured way. Otherwise, we'll end up having more failures than we'd care to see, and we could end up back in the stop-start way that we used to be. I don't think that possible negative outcome is going to happen, though. I think government, particularly defence, but also more broadly, are waking up at the moment to dependency on space, the possible ways that space technology can be used to solve quite critical and pressing national problems, whether it be national security or Great Barrier Reef monitoring or agricultural biosecurity or whatever. And they're starting to also realise that through this miniaturised transformation of space technology and also the easier access to launch, there's no reason why Australia can't be part of this and in some niche ways be world leaders.
So that Canberra mantra of there's no future in space, which we've heard from politicians in the past, that's finally dead and buried?
I believe so. There is increasing evidence to support the opportunity for Australia in the years to come, particularly in this part of the world. Last year there was a staggering amount of money invested in space from non-government sources, and last year, if you take the US out of the equation, the Asia-Pacific region invested about half of global expenditure on space. So we're sitting in a world hotspot, and at the same time we're seeing a transformation of space technology from very, very large, single, risky and incredibly expensive satellites to fleets, formations, clusters of very agile, small spacecraft that can do very sophisticated things and yet aren't expensive. They're robust because if one has a collision or something goes wrong, you simply replenish it, and you can afford to fly mission after mission after mission and put game-changing technologies on board. For example, the quantum technologies that Australia is world leading in. And that's some of the activity that UNSW Canberra and partners are working on, put Australian quantum into space.
When you talk about Australian quantum, what are you referring to there?
There's three broad areas of quantum technologies in Australia. One is quantum computing, one is quantum communications, so ultra-secure, unhackable communications, and then there's quantum sensing, so using quantum devices to make precision measurements, orders of magnitude higher precision than ever achieved before. So it's possible to put quantum communications into space, and there is an international roadmap for developing secure global communications.
China and Europe have just launched a quantum satellite between, I think it's the University of Vienna and the Academy of Sciences in China.
And indeed, Australian scientists are participating in that project as well.
Oh, wow.
But there are opportunities in Australia and expertise and know-how, particularly here in Canberra, for developing a quantum ground station that can exchange encryption keys, quantum keys, between the ground and space. And we're working with National University of Singapore to do a mission where we demonstrate the ability to exchange quantum keys from one satellite to another over very large distances. As we get both of those demonstrations closer and closer to reality, Australia will become one of, if not the leader in global secure communications capability. And that has ramifications for both security issues, but also for the finance sector.
And that's the show for now. You can subscribe and download SpaceTime as a free twice-weekly podcast through iTunes, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audio Boom, and from spacetimewithstuartgary.com. The show's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C.
This is SpaceTime with Stuart Gary. For more, you can follow us on Facebook, Twitter, and Tumblr. Just search for SpaceTime with Stuart Gary.